Okay, so this is page M388, and this is called Elephants in the Room, and we're looking at time, years, and elephant populations. Okay, this asks us to estimate an exponential function for each population changes over time and explain how you determined your function. For population A, I graphed the points. I suppose maybe you could make an upside down exponential function. This, to me, a model that would fit this better is what's called a logistic, which we'll save for the years to come. So we are going to skip over making an exponential function for this one. But for population B, I picked 2 points off my graph here. And I just chose the y-intercept and said it's about 0, 150. And I chose the point at 2 because it looked to be about 60. You can choose whichever points you want, but those two seem to be kind of the closest to the curve that they came up with. So we did regression lines before, and this is kind of like a regression curve. So like a line of best fit, but this is kind of a curve of best fit. To figure this out, I am going to now pick my points. Well, we know that A is our y-intercept. I'm not doing any transformations or shifts on here. So I'm just going to make A my y-intercept. Oftentimes the asymptote is shifted up. So we need to be careful about making that our y-intercept. But because it doesn't give me any indication of an asymptote above the axis, I can feel free to make this be 150. If it gives me an indication that the asymptote is above the axis, again, which will get saved for later classes, we'll have to adjust our A to take that into account and then put the plus D on the end here. But now I need to figure out B, okay? X and Y can take any values. There's an X that's 1, there's an X that's 3. We could have an X that's 3.5. But as we look at this, we're going to pick this one. And I'm going to use this particular one to get my B value. So I'm going to substitute in 60 for Y and 2 for X. So I get 60 equals 150 B to the second. Now this is going to allow me to solve for B and fill in B in this equation. Remember that when we work out problems, we use PEMDAS, the order of operations. Addition and subtraction and multiplication are kind of the same level. Multiplication, division are the same level. Addition, subtraction are the same level. And when I'm solving an equation, it's kind of like taking it apart. So I'm actually working backwards. When I take something apart, I go in the reverse order that I put it together. So I look at my equation, I don't see any addition subtraction. But I do see some multiplication right here, 150b squared. I also see an exponent. But since I'm working backwards, my multiplication must be undone before I deal with my exponent. I can reduce this fraction to not 3/5, 2/5, and cancel the zeros, and then 6 and 15, I can both take a 3 out of. So that gives me 2/5. And that's going to equal B squared. My 150s kind of cancel out. And 60 over 50, or 150 is 2/5, or 0.4. In order to solve this, to get just B, because I really want just B, not B squared, I'm going to take the square root of both sides. To undo the squared, I take the square root. And that gives me just B on the right side. I'm going to go to a calculator and get the square root of 2/5. And that gives me 0.632. So that means my equation or my model is 150 times 0.632 to the power of x. I can see this is an exponential decay model, and because this b is less than 1, and that my y-intercept is 150. And that's simply all I'm going to describe about my function here in part 2. So that is page M388.